Good evening, all. Welcome to today's live discussion session for the NPTEL course Water Supply Engineering. I am Reshma R, PMRF Research Scholar from Hydraulics and Water Resource Engineering Division, Department of Civil Engineering, IIT Madras. I'll share my screen now. Hope it is visible to everyone.
Yes, it is visible.
Okay. Okay. So let's start the session for today. So question number one. The primary goal of the drinking water treatment process is option A, complete removal of total solids, option B, removal or inactivation of pathogenic microorganisms, option C, complete destruction of all microorganisms, option D, all of the above. Please type in your answers in the chat box. So, what is the primary goal of drinking water treatment process? Okay. So, the correct answer is option B, that is removal or inactivation of pathogenic microorganisms. So, the primary objective of water treatment process is the removal or inactivation, either complete removal or inactivation, that is making the pathogenic microorganism, that is disease causing microorganism, to an inactive state so that waterborne diseases are not spread. So to ensure that, we'll either remove or make the pathogenic microorganisms inactive. So, this is particularly achieved through the process of disinfection, which includes removal, inactivation, or killing of pathogenic microorganisms so that they are not infectious to humans and animals. That is, the waterborne diseases are not spread. Okay. And the most important treatment step when it comes to a groundwater or surface water source is the disinfection, because there are many chances that these water sources might have active pathogenic microorganisms. So disinfection is a primary step that is to be followed when we are treating groundwater as well as surface water. Now, coming to question number 2. Disinfection is typically preferred over sterilization in water treatment because option A, sterilization is far more expensive than disinfection. Option B, disinfection provides adequate safety from the risk of waterborne diseases. Option C, sterilization also kills the microorganisms that are beneficial for humans. Option D, all of the above. So, in the normal public water treatment systems, we usually go for disinfection rather than sterilization. Sterilization is typically done in hospitals and certain industries, but not for public water supply systems. So, why do we prefer disinfection over sterilization? Okay. So the correct answer is option B, all of the above. That is, sterilization is much expensive. Yes, it is very expensive, and it is often unnecessary for public water treatment plants. The As we saw earlier, the objective of disinfection is to remove, inactivate, or kill the microorganism that is harmful to human or animal, so that we can ensure that the waterborne diseases are not being spread through the use of that particular water. So that is the primary aim of disinfection. Now when it comes to sterilization, it is the complete removal or complete destruction of all the microorganisms that is present in water. But the thing that we need to consider is that though disinfection does remove or inactivate the harmful microorganisms, the level of safety or security that we achieve through sterilization won't be achieved in the case of disinfection. But disinfection does provide adequate cleanliness. It may not necessarily inactivate all forms of microorganisms. For example, bacterial spores may not be inactivated, but it provides adequate cleanliness that is sufficient for using water for domestic and industrial purposes. Now, what is bacterial spores? They are the most dormant form of bacteria. Like they will have minimum activities including minimum metabolism, respiration, enzyme production, everything will be minimum. They will be the most dormant stage. It is the most dormant stage, and these almost inactive kind of bacterial spores won't be removed through disinfection, but still it will give adequate protection. Sterilization is something what is called extreme cleanliness. So what happens is it will remove all the microorganisms, and sometimes even the useful ones may also get destroyed. And sterilization is usually used in the case of hospitals where we need to sterilize medical instruments. There we need to ensure that there is no single microorganisms that is alive or active in that water. So in that cases, and in some particular industrial sectors, we may need such kind of water, and there only we use sterilization. Hope that is clear. So moving on to the third question: which of the following is not a chlorine based disinfectant? Option A, chlorine gas. Option B, chloramine. Option C, chlorine dioxide. Option D, chlorine trifluoride. So, which of the following is not a chlorine based disinfectant? So, when it comes to disinfection, chlorine is a major, major method. Chlorination is the major method that we use for disinfecting the water. Usually, in the case of public water supply and all, we usually go for chlorination. But among the four that is given in the options, one is not a chlorine based disinfectant. So, which is that? So, you can type in your answers in the chat box. Okay, I have two answers, C and B. Okay, so let's see which is the correct answer. The correct answer is option B, that is chlorine trifluoride. So, as I told you, that like chlorine is the most common disinfection method that we use in water treatment, and it can be used in different forms. For example, it can be inject as a chlorine dioxide, chlorine gas, hypochlorite, chloramine, etc. But this last option, that is fourth option, chlorine trifluoride, it's actually a colorless, poisonous, and highly reactive gas. It is not used as a disinfectant. It is a poisonous gas. It is a colorless gas, but it's highly reactive and it is not used as a disinfectant. Why it is not used as a disinfectant? It's because it is poisonous. So, if for a material to be used as a disinfectant, it needs to have certain characteristics. So this poisonous characteristic of chlorine trifluoride makes it unfit to be used as a disinfectant. Now, other modes of disinfecting water, that is, there are physical methods, chemical methods, and radiation methods for disinfecting water. So, by physical methods, we mainly mean filtration or boiling. That is the common process that we adopt in household for making water fit for drinking. We usually boil it. So that is one of the method for disinfecting the water. So another method is radiation method, where we make use of ultrasonic, electronic, or UV radiation to remove the bacteria and other microorganisms, pathogenic microorganisms typically, that is disease causing microorganisms, from water. And also we have chemical methods, like chlorination comes in the chemical method. So other chemical methods are ozonation or by adding other chemical agents. So the properties of an ideal disinfectant are, one thing, it should have a broad spectrum. That is, it should be active against all microbes. So the spectrum over which that particular disinfectant act should be long enough that different, like particular water sample may contain different kind of microbes, different kind of pathogenic microorganisms, so that particular disinfectant that we are using should be able to remove all of these. So it should have a broad spectrum of active region. Then it should have fast kinetics. That is, it should produce rapid inactivation. The reaction should be faster. Once we apply disinfectant, at the earliest, it should be able to inactivate or remove or kill the pathogenic microorganisms. So the third property is, it should be non-toxic, non-flammable, non-explosive. So once we are adding this disinfectant to water, it should not create any poisonous or toxic nature to the water. It should not inject any toxic nature to the water. Also, it should be non-flammable and non-explosive, so that it can be used carefree. Then, next property is, it should be effective in the presence of interfering constituents. So, in a water sample, we may not be able to judge always the different components that it may have. So, when it comes to groundwater, it may have arsenic, other elements, many elements will be there, many components will be there. So, the disinfectant that we are using should be able to react even even the presence of interfering components. Also, it should be compatible with various materials and surfaces, so that we can use it as a universal agent. We can apply it to all kind of water samples. Another important parameter is, it should be stable for intended exposure period. That is, it should have a stable criteria that it will be present in the water sample for a set period of time, so that it ensures complete removal or inactivation of all the microbes present. And another important parameter is, it, if desirable, it should be able to produce residual means, after once all the microorganisms that was present in the water sample is removed, some amount of disinfectant should be remaining, so that to protect from any future contamination, that is future possible contamination. If it happens, this residual can act there and then again disinfect the water sample. So if desirable, it should be able to produce residual. And another thing is, easy to generate and apply, so that it becomes economical. Okay. So these are the properties of an ideal disinfectant. So since the chlorine trifluoride, as we saw earlier, is a non-toxic, I mean, as is a toxic element, with a toxic compound, we cannot use it as a disinfectant. Okay, so moving on to the fourth question. Which of the following disinfectants provide a residual to ensure future protection? Option A, UV radiation. Option B, ozone O3. Option C, chloramines. Option D, boiling. So, which of the following will provide a residual to ensure future protection? Okay. So, the correct answer is option C, chloramines. So, although the chloramines are weak oxidants, but they do provide a stable residual. So, once the chloramine is added to the water sample, after removing all the present microorganism, it will remove it will first remove all the present microorganisms, and then some amount will be left behind as residual to protect from future contamination. The other options, that is UV radiation and ozone, they both do not leave any residual, and as we know, boiling definitely it doesn't have any residual characteristic. During the time of boiling only, the microorganisms will be killed. So the properties of common disinfectants. So there are certain compounds that we use as common disinfectant. So we will see the properties of each of them. So first one is free chlorine. Free chlorine will produce strong and stable hypochlorous acid HOCl and hypochlorite ion, that is OCl minus, and both of these will provide residual protection. Like it will provide residual, and then it will ensure future protection from future contamination. So when we add free chlorine to a water, whether it will produce hypochlorous acid or hypochlorite ion depends upon the pH of the water sample. At lower pH, hypochlorous acid will dominate, whereas at higher pH, hypochlorite ions will dominate. The next one is chloramines. Chloramines are weak oxidants again, but they do provide stable residual. Another one is chlorine dioxide. It is very strong oxidant, but it is highly unstable. Now, the next disinfectant that we commonly use is ozone. The problem is it is very strong oxidant, but it doesn't produce any residual because it is highly reactive and is too volatile. Then UV radiation, it is the most effective method, but it is very costly, and it primarily damages the nucleic acids of the microorganisms. It usually works at low intensity monochromatic radiation at 254 nanometer, which is usually produced by low pressure mercury lamp, or at higher intensity polychromatic radiations, which is produced by medium pressure mercury lamp. So it can work both at the low intensity monochromatic radiation as well as the higher intensity polychromatic radiations. Next one is boiling, that we adopt in households. It is effective in killing microorganisms, but associated energy and environmental cost will be high. Also, there is no residual protection So except for the chlorination process through different chemical agents, we don't have a residual for ozonation, UV radiation or boiling. Moving on to the next question. A first order degradation model is typically used to denote the disinfection kinetics of the death of microorganisms. Select the correct expression explaining the disinfection kinetics if n signifies the remaining number of viable microorganisms and t is the time taken. So if n is the remaining number of viable microorganisms and t is the time taken, which of the equations denote the disinfection kinetics of death of microorganisms? Option A, dn by dt is equal to minus n raised to k. Option B, dn by dt is equal to kn. Option C, dn by dt is equal to minus kn. Option D, none of the above. Okay, I have two different answers in the chat box. So the correct answer is option C, dn by dt is equal to minus kn. So the death of microorganisms or the disinfection kinetics, it is usually considered as first order reaction with respect to time. And the remaining number of viable microorganisms decreases with time. That is, as the time passes, the remaining number will keep on decreasing. So definitely we'll have a negative sign in the equation. And the equation is dn by dt is equal to minus kn. It's a first order reaction. Where this in this equation, k represents an empirical constant, which is a function of type of microorganism, pH, as well as the disinfectant used. So moving on to the next question, it's a numerical problem. Reverse osmosis based water treatment unit is installed to treat 12 million liter per day of water having a TDS total dissolved solids of 1500 ppm. ppm is parts per million, one of the units. So determine the TDS in gram per liter in the RO reject if the desired ppm level in the treated water is 40 ppm and the RO unit rejects 40% flow. So here we have a water treatment plant. It is supposed to treat 12 mld of water which is having 1500 ppm of total dissolved solids. So we are asked to determine the TDS in the RO reject water. So once the treatment is over, a portion will be rejected, and here this RO unit rejects 40% of the flow. And it is also given that the desired ppm level in the treated water is 40 ppm. So in the treated water it should be 40 ppm. In total we had 1500 ppm and 40% of the flow is being rejected. So what will be the amount of total dissolved solids in the RO reject? So I'll give you 2 minutes time to solve it. So it's a numerical problem. You can type in the value in the chat box once you have done. Okay, so we'll see how to solve the problem. Okay. So the correct answer is 3.69 gram per liter. So we are given that the quantity of water to be treated is 12 million liter per day, and that water is having a TDS of 1500 ppm. Also, it is mentioned that desired ppm level in the treated water, or desired TDS level, sorry, desired TDS level in the treated water is 40 ppm. The desired TDS level is 40 ppm, and the flow rejects 40 percentage of the RO unit rejects 40 percentage of the flow. So the TDS in the reject will be 1500 minus this 1500 minus zero point 0.6 into 40, that is 60 percentage of the flow is treated, and that treated water has 40 ppm TDS level. So deducting that divided by our 40 percentage flow, that will be there in our 40 percentage flow. So it is 3690 milligram per liter, which is equal to 3.69 gram per liter. Is that clear? Okay, so we'll move on to the next question. Question number 7. Identify the chlorine residual forms A, B, C available at different pH levels when chlorine is added to water for disinfection. Option A HOCl, B Cl2, C OCl minus. Option B ACl2, B HOCl, C OCl minus. Option C ACl2, B OCl minus, C HOCl. And option D A OCl minus, B HOCl, C Cl2. So which is the correct formation depending upon the pH? So in the previous question we had seen, depending upon pH, whether hypochlorous acid or hypochlorite ion will be formed. So which is the correct option? So pH is there on the x-axis. So as the time passes, as the pH varies, uh, which all chlorine residuals will be formed. Okay, the correct answer is option B, that is A chlorine, B HOCl, and C OCl minus. So as we had seen earlier, the interconversion of HOCl as well as OCl minus are pH dependent. At lower pH, that is pH less than 7.5, HOCl or hypochlorous acid will dominate, whereas when the pH is greater than 7.5, hypochlorite ions will dominate. So, and the chlorine, it will be available at very low pH, that is when the pH is below 4. So the chlorine reactions in water is, this is how it will be. At very low pH, that is less than 4, we have chlorine. Then 4 to 7.5, we will have hypochlorous acid, and then hypochlorite ions. Next question, question number 8. Which of the following disinfectants has the least propensity to produce disinfection byproducts? A. UV radiation, B. Chlorine dioxide, C. Ozone, D. Chlorination. E. Chloramination. Which of the following disinfectants has the least propensity to produce disinfection byproducts? Option A, option B, C, option C, B, and option D, E. Okay, so the correct answer is option A. There is no significant byproduct issues are generated during disinfection with UV radiation, whereas chlorine dioxide may produce chlorate and chloride ions. Disinfection with ozone may lead to bromide formation in water with high bromide concentration, and chlorination leads to the formation of trihalomethanes and trihaloacetic acids. It may also lead to some byproduct issues for specific cases. So, when we choose a disinfectant for a particular application, there are certain factors to be considered. For example, does it produce trihalomethane? Does it produce some troublesome byproducts? Is it impacted by lime softening? Is it impacted by turbidity? Does it meet Giardia removal standards or cryptosodium removal standards? Can it remove virus? What is the operator skill level that is required? Is it applicable to large utilities or small utilities? So depending upon that, we'll select among chlorine, chlorine dioxide, chloramine, ozone, and UV radiation. So we'll see what is our application, which all factors are to be considered, and then appropriately select the disinfectant. So question number 9. Photocatalysis, sonolysis, and electrochemical oxidation are different types of option A, membrane process, option B, electrodialysis process, option C, advanced oxidation process, option D, adsorption process. So, among these, which is which consists of photocatalysis, sonolysis, and electrochemical oxidation. Okay. So the correct answer is option C, advanced oxidation process. Photocatalysis, sonolysis, Fenton based, ozone based process, electrochemical oxidation, wet oxidation, supercritical water oxidation, electron beam irradiation, etc. All are different types of advanced oxidation process. So the advanced oxidation mechanisms and types are as given in the chart. So it consists of photocatalysis, Fenton based, sonolysis, ozone based process, electrochemical oxidation, which includes anodic oxidation, electroferron, photoelectrocatalysis, photoelectrofenton, etc. So these are all different kinds of advanced oxidation mechanisms. Question number 10. Match the following disease groups with an appropriate example of each category. So, in column 1, we have different diseases: malaria, schistosomiasis, typhoid, worm infection. And in column 2, we have different disease groups: waterborne disease, water washed disease, water based disease, water related vector borne disease. So, option A, A4, B3, C1, D2. Option B, A4, B3, C2, D1. Option C, A3, B4, C1, D2. Option D, A4, B2, C1, D3. So, which is the correct option? Match the disease groups with the example. Okay, we'll see. So the correct answer is option A, A4, B3, C1, and D2. That is infections spread through contaminated water. That is waterborne disease. Examples are typhoid, diarrhea. Now, the disease that is spread due to the lack of proper hygiene and sanitation. That is what is called water based disease. Example, roundworm or hookworm infections. Third one is infections that is transmitted through aquatic invertebrate organisms. I think there is a mistake in the explanation that I have typed in. So this is basically water washed disease. Okay, sorry. So waterborne disease are that kind of disease that is spread through contaminated water. That group of disease that is spread due to lack of proper hygiene and sanitation is water washed disease. And the ones that is transmitted through aquatic invertebrate organisms, they are water based disease. And if it is spread by insect that depend upon water for propagation, for their own movement, that is water related vector borne disease. Okay. So typhoid and diarrhea are examples for waterborne disease. Roundworm or hookworm infections are examples for water washed disease. Schistosomiasis is an example for water based disease. And malaria and Japanese encephalitis is an example for water related vector borne disease. So, here is the table that explains each type of disease, group, and an example. So, as we saw, waterborne disease, diarrhea, and typhoid comes under that. Water washed disease, ascariasis, and ancylostomiasis or hookworm infection. Water based disease, schistosomiasis. Water related vector borne disease, malaria, lymphatic filariasis, onchocerciasis, and Japanese encephalitis. Going on to the next question, question number 11. Which of the following is a major disadvantage of typical membrane based process? Option A, production of highly polluted water. Option B, demineralization of treated water. Option C, fouling and frequent replacement. Option D, all of the above. So, which is the major disadvantage of typical membrane based process? Okay, so the correct answer is option D, all of the above. So, membrane based process demineralizes the treated water and it will produce significant amount of polluted water as rejected. Also, membrane fouling is a major problem in these systems. So, we have to replace the membranes frequently. So the advantages and disadvantages of membrane-based process we look at are like first we go to advantages. So it has high performance. It requires only compact units so that it requires lesser space when compared to the conventional treatment schemes. Also, the operation is simple. Available membranes can be used to separate many kinds of contaminants, and without any chemicals, we can achieve disinfection. However, it has many disadvantages like it completely demineralizes the water. So, the complete demineralization or removal of the minerals as a whole is unhealthy. There are certain minerals that is to be present in a drinking water, for example. So, if we demineralize it completely, that can be that can be an unhealthy act. Another problem is that of membrane fouling. So the membranes that are used for the treatment process will frequently get clogged or fouled and makes it necessary to replace them on a regular basis. Another issue is a good amount of water is generated as polluted water through reject, backwashing, or concentrating the sample. So, moving on to the next question, question number 12. The volume of sludge produced per day in meter cube per day from a treatment plant producing 3,200 kilogram per day solids through a sludge stream with 2.5 percentage weight solid content and a bulk density of 1.11 kilogram per liter would be. So again, this is a numerical problem. Please solve it and then type it the answers in the chat box. I'll wait for 2 minutes. I'll give 2 minutes for solving the problem. So here we are given that per day the treatment plant is producing 3,200 kilogram of solids, and the sludge stream has a solid content of 2.5 percentage weight on weight, and the bulk density is 1.11 kilogram per liter. We need to determine the volume of sludge produced in a day. So please do the problem. Okay, so we'll see how to solve this. So the correct answer is 115.315 meter cube per day. So we are given that the amount of solids produced is 3200 kilogram per day and the solid content is 2.5 percentage. Bulk density is 1.11 kilogram per liter. So the total weight of sludge will be equal to 3200 by 2.5 percentage, that is 0.025. So per day the total weight of sludge is 1,28,000 kilogram per day. Now the volume of sludge is weight of sludge by density. So the weight divided by density will give 115.315 meter cube per day. Hope that is clear to everyone. Question number 13. The volume of sludge produced in question number, it's not 11, it's 12. The volume of sludge produced in question number 12 has a solids content of 0.9 percentage and is treated with a sludge thickening unit that increases its solid content to 3.7 percentage. The percentage reduction in the total sludge volume would be. So the like in the previous question we have calculated the volume of sludge produced. So if it has a solid content of 0.9 percentage and if it is treated with a sludge thickening unit so that its solid content increases to 3.7 percentage, then what is the percentage reduction in total sludge volume? So I'll give you 2 minutes time to solve this. Please solve and type in the answer in the chat box. Okay, so we'll see how to solve the problem. The correct answer is 75.676 percentage. It's given that the amount of solids produced is 3200 kilogram per day, as we saw in the previous question. Solid content in the sludge stream is 2.5 percentage, and the bulk density was 1.11 kilogram per liter. So the sludge volume from the thickener is the total volume, that is 115.315, that we got from the previous question. It is mentioned that 0.9 percentage solid content is there, which is increased to 3.7 percentage. So the sludge volume from the thickener will be 115.315 into 0.009 by 0.037, which gives you 28.049 meter cube per day. So the percentage reduction is 115.315 minus 28.049 divided by 115.315 into 100, which gives you 75.676 percentage. That is the percentage reduction in sludge volume. Hope that is clear.
Would you please repeat that sludge volume from thickener?
Yeah. So in the question, if you look, yeah. So in the question, it is mentioned that the volume of sludge produced in question number 12, that is here, the volume of sludge produced was 115.315 meter cube in a day. Now, in this question, it is mentioned that that particular volume has a solid content of 0.9 percentage, that is 0.009. Now, when we are treating it with a sludge thickening unit, this increases to 3.7 percentage. So, when it is solved, the sludge volume at the end after treatment from the thickener, it becomes, this was the initial one, it becomes 115.315 into 0.009. So, this is the inlet to the thickener, and when it comes out the sludge volume becomes 3.7, the solid content becomes 3.7 percentage, so the sludge volume becomes 28.049 meter cube. So we know the initial sludge volume and the final sludge volume now. So to determine the percentage reduction, initial minus final by initial into 100 will give you a value in percentage. Is that clear?
Yes.
Okay. So we'll move on to the next question. Determine the required chlorine dosage if the CT value for the desired disinfection with chlorine was estimated as 62 milligram minute per liter and 5 million liters per day of water was to be treated in a 15 meter cube disinfection tank. So please solve it. Okay, so we'll see how to solve the problem. The correct answer is 14.35 milligram per liter. So it's given that CT value is 62 milligram minute per liter and the flow is 5 million liters per day, that is 5000 meter cube per day, or 208.333 meter cube per hour. So the contact time is given by 15 by 208.333, which is 0.072 hours or 4.32 minutes. Therefore, the chlorine dose, that is CT by T, that is CT value by contact time, will give the chlorine dosage. So 62 by 4.32, which is 14.35 milligram per liter, is the required chlorine dose. Hope that is clear. Moving on to the next question. Question number 15. So it is the same, the values are same, that is the same CT value, that is 62 milligram minute per liter, and 5 mld of water was to be treated in a 15 meter cube disinfection tank. So if the disinfection process resulted in 1.35 milligram per liter residual chlorine, determine the chlorine demand of the water. So in addition to the previous question, the residual chlorine value is also given and we need to determine the chlorine demand. So quickly calculate that. It just need a 1 minute time for the calculation. Okay, so we'll see how to solve it. So the correct answer is 13 milligram per liter. So it's given that CT value is 62 milligram minute per liter. The flow to be handled is 5 mld, that is 5000 meter cube per day, or 208.333 meter cube per hour. Chlorine dose is 14.35 milligram per liter and chlorine residual is 1.35 milligram per liter. This chlorine dose we had calculated in the previous question. So now to determine the chlorine demand is given by chlorine dose minus chlorine residual. That is 14.35 minus 1.35, which is equal to 13 milligram per liter. So with that, uh, the questions for today is done. So I'll stop sharing the screen. So if you have any doubts, please ask. Or else we can stop the session for today and then we'll meet again in the next discussion session. Okay. Thank you all. So we'll meet again in the next discussion session on next Tuesday.